Hello and welcome. In this video, we will explore definite integrals, a fundamental concept in calculus with wide-ranging applications. By the end of this session, you will be able to define and calculate definite integrals using the fundamental theorem of calculus, apply key properties of definite integrals to simplify calculations, and solve problems involving definite integrals using substitution. Let's begin with an opening problem to set the context. Consider the intensity of light entering a greenhouse. On a sunny day, the intensity is given by the function I equals 3 sine of pi t over 10. On an overcast day, it's I equals sine of pt over 10. Here t is the number of hours after sunrise from 0 to 10. The graphs of these two functions are shown here. The higher curve, C1, represents the sunny day, and the lower curve, C2, represents the overcast day. The shaded area between them represents the difference in light intensity over time. This problem asks us to find this shaded area. If light intensity is the rate of energy transfer, what does this area represent? This question leads us directly to the concept of definite integrals, which are used to calculate the area under a curve and the net change of a quantity given its rate of change. Let's formalize this idea. We've previously encountered the fundamental theorem of calculus, which connects differentiation and integration. For a continuous function f of x, with an antiderivative f of x, the definite integral from a to b of f of x dx is equal to f of b minus f of a. This is the core definition of a definite integral. It represents the net change of the antiderivative f of x over the interval from a to b. Geometrically, if f of x is non-negative, this value is the area under the curve of f of x from x equals a to x equals b. We read this expression as the integral from a to b of f of x with respect to x. The numbers a and b are called the lower and upper limits of integration, respectively. A key point to remember is that when calculating definite integrals, we can omit the constant of integration, c. This is because it will always cancel out in the subtraction process, f of b minus f of a. We often use a shorthand notation for f of b minus f of a. We write it as a square bracket with f of x inside, and the limits a and b on the right side. So the definite integral is equal to this expression, which simplifies to f of b minus f of a. Now, let's look at some essential properties of definite integrals that will help us solve problems more efficiently. First, if you swap the limits of integration, the sign of the integral changes. Second, you can pull a constant k out of the integral. Third, you can split an integral over an interval a to c into two integrals, from a to b and from b to c. And fourth, the integral of a sum of functions is the sum of their integrals. These properties are direct consequences of the fundamental theorem of calculus and the properties of antiderivatives. They are powerful tools for manipulating and simplifying integrals. Let's apply these concepts to some examples. Our goal here is to practice the process of finding an antiderivative and evaluating it at the limits. First, let's find the definite integral from 1 to 2 of the polynomial x cubed minus 4x plus 5. Step 1 is to find the antiderivative of the function inside the integral. Using the power rule for integration, the antiderivative of x cubed is x to the 4th over 4. The antiderivative of 4x is 4 times x squared over 2, which simplifies to 2x squared. And the antiderivative of 5 is 5x, so our antiderivative is 1/4 x to the 4th minus 2x squared plus 5x. Step 2 is to evaluate this antiderivative at the upper and lower limits and subtract. We write our antiderivative in the bracket notation. First, we substitute the upper limit, 2, into the expression. Then we subtract the result of substituting the lower limit, 1. Now we just need to simplify the arithmetic. The first part simplifies to 16 over 4, which is 4 minus 8 plus 10. The second part is 1 over 4 minus 2 plus 5. This gives us 6 minus 3 and 1/4, which is 11 over 4, so the value of the definite integral is 11 over 4. Let's try another example, this time involving fractional and negative exponents. We need to find the integral from 1 to 4 of 2 times the square root of x plus 3 over x. First, let's rewrite the function using exponents to make integration easier. The square root of x is x to the power of 1/2, and 3 over x is 3 times x to the power of -1. So our integral is from 1 to 4 of 2x to the 1/2 plus 3x to the -1. Now let's find the antiderivative. For the first term, we add 1 to the exponent to get 3/2 and divide by 3/2, which is the same as multiplying by 2/3. This gives us 4/3 to the 3/2. For the second term, the antiderivative of 1 over x is the natural logarithm of the absolute value of x. So we have 3 ln of the absolute value of x. Now we evaluate this antiderivative at the limits. We substitute 4, the upper limit, and subtract the result of substituting 1, the lower limit. The absolute value signs are not necessary here since our limits are positive. Let's simplify. Remember that 4 to the 3/2 is the square root of 4 cubed, which is 2 cubed, or 8. And the natural log of 1 is 0. So we have 4 to the 3 times it, plus 3 ln 4 minus 4/3. This simplifies to 28/3 plus 3 ln 4. Using logarithm properties, 3 ln 4 is the same as ln of 4 cubed, or ln 64. So our final answer is 28/3 plus ln 64. Our next example involves a trigonometric function and radian measure. We need to find the integral from 0 to pi over 3 of sine of 2 sec. To find the antiderivative of sine of 2 pi, we can use a simple substitution or recall the chain rule in reverse. The antiderivative of sine of u is negative cosine of u. Because of the two values inside the sine function, we need to divide by the derivative of 2x, which is 2. So the antiderivative is negative 1/2 cosine of 2x. Now we evaluate this antiderivative at the limits. We substitute pi over 3 and 0 into our antiderivative and subtract. This gives us negative 1/2 cosine of 2 pi over 3 minus negative 1/2 cosine of 0. Let's recall the values of these trigonometric functions. Cosine of 2 pi over 3 is negative 1/2, and cosine of 0 is 1. Substituting these values, we get negative 1/2 times negative 1/2 plus 1/2 times 1. This simplifies to 1/4 plus 1/2, which equals 3/4. So the value of the integral is 3/4. Sometimes, finding an antiderivative analytically can be difficult or even impossible. In these cases, we are expected to use a graphics calculator to evaluate the definite integral. Let's look at an example. We want to evaluate the integral from 2 to 5 of x times e to the power of x, correct to 4 significant figures. This integral requires a technique called integration by parts, which we will cover later. For now, let's see how to solve it using a calculator. Most graphics calculators have a function to compute definite integrals. You typically input the function, the variable of integration, and the upper and lower limits. For example, on a Casio calculator, you might use the integral symbol from the calculus menu. On a TI-84, you might use the fnint function. On a TI-Nspire, you can use the integral template. After inputting the expression, the calculator will display the numerical value of the integral. In this case, it's approximately 586.2635803. The problem asks for the answer correct to 4 significant figures. Rounding our result to 4 significant figures, we get 586.3. It's crucial to pay attention to the required precision in IB exams. Now let's return to the properties of definite integrals and see how they can be used to solve problems. Suppose we are given that the integral of f of x from 1 to 3 is 2, and the integral from 1 to 6 is negative 3. We need to find the integral from 3 to 6. This problem can be solved using the third property we discussed, the interval addition property. The property states that the integral from a to c is the sum of the integral from a to b and the integral from b to c. In our case, a is 1, c is 6, and b is 3. So, the integral from 1 to 6 is equal to the integral from 1 to 3 plus the integral from 3 to 6. Now we can substitute the given values and solve for the unknown integral. We have negative 3 equals 2 plus the integral from 3 to 6. Subtracting 2 from both sides, we find that the integral from 3 to 6 of f of x dx is negative 5. This demonstrates how understanding the properties of integrals can simplify complex problems into straightforward algebra. Another important application of definite integrals is in proving properties related to even and odd functions. First, let's recall the definitions. An even function is symmetric about the y-axis, meaning f of negative x equals f of x. An odd function is symmetric about the origin, meaning f of negative x equals negative f of x. Let's prove a property for odd functions. We want to prove that if f is an odd function, the integral from negative a to a is 0. We can split the integral into two parts. The integral from negative a to a is the integral from negative a to 0 plus the integral from 0 to a. Now, let's focus on the first integral. We'll use a substitution. Let u equal negative x, then do equals negative dx. When x is negative a, u is a. When x is 0, u is 0. And since fe is odd, f of negative x is negative f of x. Substituting these into the first integral, we get the integral from a to 0 of negative f of x times negative do. The negatives cancel, and we can swap the limits by adding a negative sign. This gives us negative the integral from 0 to a of f of x du. Since the variable of integration doesn't matter, this is negative the integral from 0 to a of f of x d. Now, let's substitute this back into our original equation. We have negative the integral from 0 to a plus the integral from 0 to a. These two terms cancel out, proving that the integral is 0. This makes sense visually. The area above the x-axis on one side of the origin is exactly canceled by the area below the x-axis on the other side. A similar proof can be constructed for even functions, showing that the integral from negative a to a is twice the integral from 0 to a. These properties are very useful for simplifying integrals over symmetric intervals. Next, we'll tackle a powerful technique for evaluating integrals. Substitution. This is the reverse of the chain rule for differentiation. When we use substitution with definite integrals, there's a crucial step. We must convert the endpoints of the integral to the new variable. If we don't, our answer will be incorrect. Let's evaluate the integral from 2 to 3 of x over x squared minus 1. We look for a part of the function whose derivative is also present. Here, the derivative of x squared minus 1 is 2x, and we have an x in the numerator. So we let u equal x squared minus 1. Differentiating with respect to x, we get d du dx equals 2x. Rearranging, we find that x dx is equal to 1/2 du. Now for the critical step, converting the limits. When x is 2, u is 2 squared minus 1, which is 3. When x is 3, u is 3 squared minus 1, which is 8. Our new limits are 3 and 8. Now we can rewrite the entire integral in terms of u. The integral becomes the integral from 3 to 8 of 1 over u times 1/2 du. We can pull the 1/2 out, leaving us with 1/2 times the integral from 3 to 8 of 1 over u du. This is a much simpler integral to solve. The antiderivative of 1 over u is the natural logarithm of the absolute value of u. Evaluating from 3 to 8, we get 1/2 times the quantity ln 8 minus ln 3. Using logarithm properties, this simplifies to 1/2 ln of 8 over 3. Let's do another substitution example, this time with a trigonometric function. We want to evaluate the integral from pi over 6 to pi over 2 of the square root of sine x times cosine x. Again, we look for a function and its derivative. The derivative of sine x is cosine x, which is present in the integral. So we let u equal sine x. Then do dx equals cosine x, which means cosine x dx is equal to du. Now let's convert the limits of integration. When x is pi over 6, u is sine of pi over 6, which is 1/2. When x is pi over 2, u is sine of pi over 2, which is 1. Our new limits are 1/2 and 1. Now we can rewrite the integral in terms of u. The integral becomes the integral from 1/2 to 1 of the square root of u du. We can write the square root of u as u to the power of 1/2. Let's find the antiderivative and evaluate. Using the power rule, the antiderivative of u to the 1/2 is u to the 3/2 divided by 3/2, which is 2/3 u to the 3/2. Evaluating from 1/2 to 1, we get 2/3 times 1 to the 3/2, minus 2/3 times 1/2 to the 3/2. Simplifying the expression. This gives us 2/3 minus 2/3 times 1 over 2 root 2. This simplifies to 2/3 minus 1 over 3 root 2. We can rationalize the denominator to get 2/3 minus root 2 over 6. This is our final exact answer. Let's revisit our opening problem. We can now solve it using definite integrals. The problem asks for the shaded area between the sunny day curve C1 and the overcast day curve C2 from t equals 0 to t equals 10. The area between two curves is found by integrating the difference between the upper curve and the lower curve over the given interval. In our case, the area is the integral from 0 to 10 of the sunny day intensity minus the overcast day intensity. Substituting the functions, we get the integral from 0 to 10 of 3 sine of pi t over 10 minus sine of pi t over 10. We can simplify the integrand. The integral simplifies to the integral from 0 to 10 of 2 sine of pi t over 10 dt. Now, let's find the antiderivative. The antiderivative of sine of kx is negative 1 over k cosine of kx. Here, k is pi over 10. So the antiderivative is 2 times negative 10 over pi cosine of pi t over 10, which is negative 20 over pi cosine of pi t over 10. Finally, we evaluate at the limits. We substitute 10 and 0. This gives us negative 20 over pi times cosine of pi, minus negative 20 over pi times cosine of 0. Cosine of pi is negative 1, and cosine of 0 is 1. So we have negative 20 over pi times negative 1 plus 20 over pi times 1. This is 20 over pi plus 20 over pi, which equals 40 over pi. The area is 40 over pi square units. The problem also asked what this area means. If intensity is the rate of energy transfer, then the integral of intensity over time gives the total energy transferred. So, the area of 40 over pi represents the total additional energy from light that the greenhouse receives on a sunny day compared to an overcast day over that 10-hour period. Let's recap what we've learned. We started by defining the definite integral using the fundamental theorem of calculus, which connects it to the net change of an antiderivative. We saw how to calculate definite integrals by finding an antiderivative and evaluating it at the limits of integration. We also explored key properties that allow us to manipulate and simplify integrals. We then learned the powerful technique of substitution, emphasizing the critical step of converting the limits of integration. Finally, we applied these concepts to solve a real-world problem involving the area between two curves. You are now equipped to define and calculate definite integrals, apply their properties, and use substitution to solve problems, which are essential skills for the IB/AAHL curriculum. To solidify your understanding, here are 5 practice questions in the style of IB assessment. Pause the video, work through them, and then resume to see the fully worked solutions. Question 1. Find the exact value of the integral from 0 to 1 of x squared plus 2x plus 1. Question 2. Evaluate the integral from 0 to pi over 4 of cosine of 2x. Question 3. Use substitution to find the integral from 0 to 1 of 3x squared times the quantity x cubed plus 1 squared. Question 4. Given that the integral from 1 to 4 of f of x dx is 5, find the integral from 1 to 4 of 2f of x minus 3. Question 5. Use your GDC to evaluate the integral from 0 to 2 of e to the power of negative x squared. Correct to 3 significant figures. Welcome back. Let's go through the solutions. For question 1, we find the antiderivative of x squared plus 2x plus 1, which is x cubed over 3 plus x squared plus x. Evaluating from 0 to 1, we get 1/3 plus 1, which is 7 over 3. For question 2, the antiderivative of cosine of 2x is 1/2 sine of 2x. Evaluating from 0 to pi over 4, we get 1/2 sine of pi over 2 minus 1/2 sine of 0. This is 1/2 times 1, which is 1/2. For question 3, we let u equal x cubed plus 1. Then do equals 3x squared dx. The limits become u equals 1 and u equals 2. The integral transforms to the integral from 1 to 2 of u squared do. The antiderivative is u cubed over 3. Evaluating from 1 to 2, we get 8 over 3 minus 1 over 3, which is 7 over 3. For question 4, we use the linearity property. We split the integral into two parts. The first part is 2 times the integral of f of x, which is 2 times 5 or 10. The second part is the integral of 3, which is 3x. Evaluating 3x from 1 to 4 gives 9, so the total is 10 minus 9, which is 1. For question 5, we use a GDC. Inputting the integral from 0 to 2 of e to the negative x squared, the calculator gives approximately 0.88208. Rounding to 3 significant figures, we get 0.882. I hope these examples and practice questions have helped you build a strong foundation in definite integrals. Thank you for watching. Hello and welcome. In this video, we will delve into more advanced techniques for evaluating definite integrals, specifically integration by parts and partial fractions. By the end of this session, you will be able to apply integration by parts to solve integrals of products of functions. Use partial fraction decomposition to integrate rational functions and solve problems that combine these techniques. These methods are essential for the IB mathematics, analysis, and approaches. Higher-level curriculum and will allow you to solve a much wider range of integration problems. Let's begin with integration by parts. This technique is used to integrate a product of two functions and is derived from the product rule for differentiation. The formula for integration by parts is the integral of u dv equals u times v minus the integral of v dE. The key is to choose u and dv wisely. A helpful mnemonic for choosing u is LIAT. LIAT stands for logarithmic, inverse trigonometric, algebraic, trigonometric, and exponential. You should choose u as the function that appears first in this list. Let's evaluate the integral from 0 to pi over 2 of x sin x dx. Using LIAT, x is an algebraic function and sin ax is a trigonometric function. A comes before t, so we choose u equals x. Let u equal x and dv equals sine x dx. Then do is dx and v is the integral of sine x, which is negative cosine x. Now we apply the formula. The integral is u times v, which is negative x cosine x, minus the integral of v I do how, which is the integral of negative cosine x dx. The two negatives cancel, so we have negative x cosine x plus the integral of cosine x dx. The integral of cosine x is sine x, so our antiderivative is negative x cosine x plus sine x. Now we evaluate this from 0 to pi over 2. Substituting pi over 2, we get negative pi over 2 times cosine of pi over 2, plus sine of pi over 2. Substituting 0, we get 0. Since cosine of pi over 2 is 0 and sine of pi over 2 is 1, the result is 1. The value of the integral is 1. Integration by parts can also be used to integrate functions that don't appear to be products, like the natural logarithm. Let's evaluate the integral from 1 to 3 of ln x dx. We can think of this as the product of ln x and 1. Using LIAT, L for logarithmic comes first, so we choose u equals ln x. Let u equal ln x and dv equal dx. Then do is 1 over x dx, and v is the integral of dx, which is x. Now we apply the formula. The integral is u times v, which is x ln x, minus the integral of v du, which is the integral of x times 1 over x dx. This simplifies to x ln x minus the integral of 1 dx. The integral of 1 is x, so our antiderivative is x ln x minus x. Now we evaluate this from 1 to 3. Substituting 3, we get 3 ln 3 minus 3. Substituting 1, we get 1 ln 1 minus 1. Since ln 1 is 0, the second part is negative 1. So the result is 3 ln 3 minus 3 plus 1, which is 3 ln 3 minus 2. Now let's move on to our second advanced technique. Integration using partial fractions. This method is used to integrate rational functions, which are fractions where the numerator and denominator are polynomials. The core idea is to decompose a complex rational function into a sum of simpler fractions that are easy to integrate. Let's evaluate the integral from 2 to 3 of x plus 4 over x squared minus 5x plus 6. First, we need to factor the denominator. The denominator factors into x minus 2 times x minus 3. So our integrand is x plus 4 over x minus 2 times x minus 3. Next, we set up the partial fraction decomposition. We assume the fraction can be written as a over x minus 2 plus b over x minus 3. Our goal is to find the constants a and b. We can find a and b by multiplying both sides by the common denominator. This gives us x plus 4 equals a times x minus 3 plus b times x minus 2. A quick way to find a and b is to choose values of x that make one of the terms 0. If we let x equal 3, the a term vanishes, and we get 7 equals b. If we let x equal 2, the b term vanishes, and we get 6 equals negative a, so a is negative 6. So our integral becomes much simpler. The integral is from 2 to 3 of negative 6 over x minus 2 plus 7 over x minus 3. The antiderivative of 1 over x plus b is 1 over ln of the absolute value of x plus b. The antiderivative is negative 6 ln of the absolute value of x minus 2 plus 7 ln of the absolute value of x minus 3. Evaluating from 2 to 3, we get 7 ln 1 minus 6 ln 1 minus 7 ln 0 plus 6 ln 0. This is problematic because ln 0 is undefined. This means the integral is improper and does not converge. The question as stated in the textbook is flawed because the function has vertical asymptotes at x.2 and x3, which are the limits of integration. For a proper definite integral, the function must be continuous on the closed interval of integration. This highlights an important point. Always check for discontinuities within the interval of integration. If a discontinuity exists, the integral is improper and requires a different approach using limits, which is beyond the scope of this video. Let's try another partial fractions example that is well defined. We'll evaluate the integral from 2 to 3 of 1 over x squared minus 1. First, factor the denominator. The denominator is a difference of squares x minus 1 times x plus 1. Next, set up the partial fraction decomposition. We write 1 over x minus 1 times x plus 1 as a over x minus 1 plus b over x plus 1. Multiply by the common denominator. This gives 1 equals a times x plus 1 plus b times x minus 1. Now, find a and b. Letting x equal 1 gives 1 equals 2a, so a is 1/2. Letting x equal negative 1 gives 1 equals negative 2b, so b is negative 1/2. So our integral becomes the integral from 2 to 3 of 1/2 over x minus 1 minus 1/2 over x plus 1. We can pull out the 1/2 and integrate. The antiderivative is 1/2 times the quantity ln of the absolute value of x minus 1 minus ln of the absolute value of x plus 1. Using logarithm properties, this is 1/2 ln of the absolute value of x minus 1 over x plus 1. Now evaluate at the limits. Substituting 3 and 2, we get 1/2 times the quantity ln of 2 over 4 minus ln of 1 over 3. This simplifies to 1/2 times ln of 1/2 minus ln of 1/3. Using logarithm properties, this is 1/2 ln of 3/2. Let's recap our advanced integration techniques. We've covered integration by parts and partial fractions. Integration by parts is for products of functions, using the Lee-at rule to choose u. Partial fractions is for rational functions, where we decompose the fraction into simpler terms. We also saw the importance of checking for discontinuities to avoid improper integrals. These methods are powerful tools that will allow you to solve a much broader range of integration problems in your IB studies. Here are 5 more practice questions to test your mastery of these advanced techniques. Work through them and then check your solutions. Question 1. Use integration by parts to find the exact value of the integral from 0 to 1 of xe to the xd. Question 2. Use partial fractions to find the exact value of the integral from 3 to 4 of 1 over x squared minus 4 dx. Question 3. Find the exact value of the integral from 1 to e of x squared ln x dx. Question 4. Find the exact value of the integral from 0 to 1 of x plus 1 over x squared plus 3x plus 2 dx. Question 5. Find the exact value of the integral from 0 to pi over 2 of x squared cosine x dx. Let's review the solutions to the practice questions. For question 1, using integration by parts with u equals x and dv equals e to the x dx, we get the antiderivative x e to the x minus e to the x. Evaluating from 0 to 1 gives 1. For question 2, we decompose 1 over x squared minus 4 into 1/4 over x minus 2 minus 1/4 over x plus 2. The antiderivative is 1/4 ln of the absolute value of x minus 2 over x plus 2. Evaluating from 3 to 4 gives 1/4 ln of 3 over 2. For question 3, using integration by parts with u equals ln x and dv equals x squared dx, we get the antiderivative 1/3 x cubed ln x minus 1/9 x cubed. Evaluating from 1 to e gives 2e cubed plus 1 all over 9. For question 4, the denominator factors to x plus 1 times x plus 2. The x plus 1 in the numerator cancels, leaving the integral of 1 over x plus 2. The antiderivative is ln of the absolute value of x plus 2. Evaluating from 0 to 1 gives ln of 3 over 2. For question 5, this requires integration by parts twice. The final result is pi squared over 4 minus 2. Well done if you got these correct. If not, review the relevant sections and try similar problems. Continued practice is key to success in calculus. Hello and welcome. In this video, we will explore the geometric applications of definite integrals, focusing on calculating areas and volumes of revolution. By the end of this session, you will be able to calculate the area between two curves, find the volume of a solid of revolution using the disk and washer methods, and solve problems that combine these concepts. These applications are a cornerstone of the IB Mathematics, Analysis and Approaches higher-level curriculum and provide a powerful way to connect calculus to geometry. Let's start with the area between two curves. We've already seen a glimpse of this in our opening problem. The general formula for the area between two curves, f of x and g of x, over an interval from a to b, is the integral from a to b of the absolute value of their difference. This ensures the area is always positive. If one function is always above the other on the interval, the formula simplifies. If f of x is greater than or equal to g of x, the area is simply the integral of the upper function minus the lower function. Let's find the area enclosed by the curves y equals x squared and y equals 2x minus x squared. First, we need to find the points of intersection to determine our limits of integration. We set the two functions equal to each other. This gives us 2x squared minus 2x equals 0, which factors to 2x times x minus 1 equals 0. The solutions are x equals 0 and x equals 1. These will be our limits of integration. Next, we need to determine which function is the upper curve on the interval 0, 1. We can test a point, say x equals 0.5. At x equals 0.5, y equals x squared is 0.25, and y equals 2x minus x squared is 0.75. Since 0.75 is greater than 0.25, the curve y equals 2x minus x squared is the upper curve. Now we can set up the integral for the area. The area is the integral from 0 to 1 of the upper curve minus the lower curve. This simplifies to the integral of 2x minus 2x squared. Finally, we evaluate the integral. The antiderivative is x squared minus 2/3 x cubed. Evaluating from 0 to 1 gives 1 minus 2/3, which is 1/3. The area enclosed by the two curves is 1/3 square unit. Now let's move on to volumes of revolution. This is a method for finding the volume of a 3D solid created by rotating a 2D region around an axis. We'll focus on two methods, the disk method and the washer method. The disk method is used when the region being rotated is flush against the axis of revolution, creating a solid disk. The washer method is used when there's a gap between the region and the axis, creating a washer-shaped slice. Let's start with the disk method. The formula for the disk method is v equals pi times the integral from a to b of the radius squared d, dx. The radius, r of x, is the distance from the axis of revolution to the curve. Let's find the volume of the solid formed by rotating the region under the curve y equals the square root of x from x equals 0 to x equals 4 around the x-axis. In this case, the axis of revolution is the x-axis, and the region is flush against it. The radius r of x is simply the function value square root of x. So, the volume is pi times the integral from 0 to 4 of the square root of x squared dx. This simplifies to pi times the integral of x dx. Now we evaluate the integral. The antiderivative of x is x squared over 2. Evaluating from 0 to 4, we get p times 16 over 2, which is 8 pi. The volume of the solid is 8 pi cubic units. Now let's look at the washer method, which is used when the solid of revolution has a hole in the middle. The formula is v equals pi times the integral from a to b of the outer radius squared minus the inner radius squared d dx. The outer radius, r of x, is the distance from the axis to the outer curve, and the inner radius, r of x, is the distance from the axis to the inner curve. Let's find the volume of the solid formed by rotating the region between y equals x and y equals x squared about the x-axis. First, we find the intersection points, which are at x equals 0 and x equals 1. These are our limits of integration. Next, we identify the outer and inner radii. On the interval 0, 1, the line y equals x is above the parabola y equals x squared. So, the outer radius, r of x, is x, and the inner radius, r of x, is x squared. Now we set up the integral. The volume is pi times the integral from 0 to 1 of x squared minus x squared squared dx. This simplifies to pi times the integral of x squared minus x to the 4th dx. Finally, we evaluate the integral. The antiderivative is x cubed over 3 minus x to the 5th over 5. Evaluating from 0 to 1 gives p times 1/3 minus 1/5. This simplifies to 2 pi over 15. The volume of the solid is 2 pi over 15 cubic units. Let's recap our geometric applications of definite integrals. We learned how to find the area between two curves by integrating the difference between the upper and lower functions. We also explored volumes of revolution, using the disk method for solids without holes and the washer method for solids with holes. The key is to correctly identify the limits of integration and the radii. These techniques are powerful tools for solving a variety of geometric problems using calculus. Here are 5 practice questions on areas and volumes of revolution. Work through them and then check your solutions. Question 1. Find the area enclosed by the curves y equals x squared and y equals x plus 2. Question 2. Find the volume of the solid formed by rotating the region under y equals x cubed from x equals 0 to x equals 1 about the x-axis. Question 3. Find the volume of the solid formed by rotating the region between y equals x and y equals the square root of x about the x-axis. Question 4. Find the area enclosed by the curves y equals sine x and y equals cosine x from x equals 0 to x equals pi over 2. Question 5. Find the volume of the solid formed by rotating the region bounded by y equals x squared, y equals 0, and x equals 2 about the y-axis. Let's go through the solutions. For question 1, the curves intersect at x equals -1 and x equals 2. The line is above the parabola. The area is the integral from -1 to 2 of x plus 2 minus x squared, which evaluates to 9 over 2. For question 2, we use the disk method. The radius is x cubed. The volume is p times the integral from 0 to 1 of x to the 6th, which evaluates to pi over 7. For question 3, we use the washer method. The outer radius is the square root of x, and the inner radius is x. The volume is p times the integral from 0 to 1 of x minus x squared, which evaluates to pi over 6. For question 4, the curves intersect at pi over 4. From 0 to pi over 4, cosine is above sine. From pi over 4 to pi over 2, sine is above cosine. We split the integral and add the absolute values of the results. The area is 2 times the square root of 2 minus 2. For question 5, we must integrate with respect to y. We rewrite the function as x equals the square root of y. The limits for y are 0 to 4. We use the disk method with radius 2 and a hole with radius square root of y. The volume is PA times the integral from 0 to 4 of 4 minus y, which evaluates to 8 pi. That concludes our exploration of definite integrals and their applications. You have now seen how to calculate them, use their properties, apply substitution, integrate using parts and partial fractions, and use them to find areas and volumes. Keep practicing these techniques to build your confidence and proficiency. Hello and welcome. In this video, we will explore the final major application of definite integrals in the IB Mathematics, Analysis and Approaches, Higher Level Curriculum, Kinematics. By the end of this session, you will be able to use integration to find displacement and total distance traveled from a velocity function, and to find velocity from an acceleration function. This application connects the abstract concept of integration to the physical world of motion, providing a powerful tool for solving problems in physics and engineering.